Hello, everyone, and thank you for joining. In this session, we are going to talk about how to build a text-to-SQL use case using Amazon Bedrock and Anthropic's Claude 3 model family. Okay, before we get started with that, I am going to set up some Jupyter themes for the dark mode. So if you like the dark mode, you can follow these steps as well. I'm using Monakai here, which is kind of give me a nice black background with some pop colors as well. Okay, so over the next 30 minutes or so in this video, I'm going to walk you through on this Jupyter notebook, where we will be discussing two different architectures and we will be building those architectures as well. So the first one is very straightforward and simple, right? We are using text-to-SQL using Amazon Bedrock. Now, if you think about the use cases, like many times you have business users, vendors. If you take an example of retail customers, right? And let's say you have this e-commerce database which is sitting in Aurora Postgres. Now, if those business users need to interact to Aurora Postgres, they will have to send the SQL queries, right? So that's what Aurora Postgres understand, or any other database for that matter, right? And previously, how it's been very popular use case, right? And previously, how did we deal with these kind of use cases? Is having some kind of a BI tool in between, which shares the dashboard reports, things like that, with the vendors and the business users. So, for example, a business user might want to know how many products he sold, or how many customers bought an item XYZ. So all of that needed to be actually showcased as part of kind of a report. Now, with the help of these LLMs, which are really good in understanding these languages and doing these human brain-like tasks, we can actually achieve all of that using Anthropic's Claude 3 models. So here again, the use case remains very similar. User send a natural language question to the model, and model actually converts that to a SQL based on what the text is and what kind of tables does it needs to actually query. It creates a SQL, executes it, got the SQL output, converts it back to the natural language, and pass it back to the user. Now, one thing that we need to track as part of this kind of architecture is invocation latency, input tokens, and output tokens. And that's something you can do easily through a Bedrock and CloudWatch integration, right? So you can track all of that. And the reason why it is important to track these things is because whenever you are building this kind of architecture, chances are you'll be spending a lot of money in your input and output tokens. So you want to make sure that you have a good way to track it and also to optimize that as well. All right, so let's start with some prerequisite installation. So I'm going to use Langchain for this Jupyter notebook as well. And Langchain is just a framework that makes it easy to build GenAI applications, a lot of integrations that makes things simpler. Let's go ahead and start some of the Langchain community tools. All good. So next we'll be also be installing the PG vector and psychopg2 binary. So psychopg2 binary helps us connect to Postgres using Python, and then PG vector is something that will be using a vector database for the second architecture, where we will be doing some similarity search. So let's go ahead and install it right away. Chase requirement already satisfied because I ran through this Jupyter notebook few times before. All right, so now that we have some of these prereqs installed, now let's see how do we connect using psychopg2. So using psychopg2, you can connect to the database with you need to provide hostname, database, user, and password. Now, well, you can give hard-coded passwords here. Obviously, not recommended to use that. So what I'm using here is a secret manager. So if you have worked with AWS, AWS has this service called Secret Manager where you can store database secrets, so username, passwords, host names, and so on. And you can easily extract that secret using the get secret value. And with that, you don't have to hard code and you can pass it securely to the application. So in this, we are just going to run it and we are going to see the table count. Basically, the idea is we wanted to see if we are able to connect to the Postgres properly and if we get the table count from database. Okay, so we have 76 table in our Postgres. Now for this particular demo, where we are building this text-to-SQL, we'll not be using all of these 76 tables. We'll be using only few tables, but at least we got the result, so that means things are looking good. Okay, so let's create a simple schema first. And here are the tables that I'm creating. So I'm creating a customer table, product category, a product table, order table, or item. So there are like 5 different tables I'm creating, kind of mimicking the retail customized schema, but very, very small scale level. And then I'm also adding few rows in all of these tables as well. So this has already been done. I cannot recreate the tables, but this is how the schema looks like. And I'll show you towards the end in Postgres how does the schema looks like as well. Okay, now once you have this schema, you can actually connect to Postgres using Langchain and check the table information. So how do we do that? So with Langchain, you get this SQL database utility with which you can actually get all of the information in part of the variable. You can actually get all of the information about the tables, table names, schemas, some sample data from this and store it in a variable. And then you can run through, for example, here if you are doing db.dialect, in that case, it will show you which database you're using, Postgres or MySQL. You can get table names, you can get more table details like schemas and DDLs. So let's run this and see it out. So here you have the dialect as Postgres. You have some of the tables that we created in the last step, customer to products. A few other tables that I created later on in this notebook, and I'll explain why this table is used. But for now, just think like we have these 5 different tables. So DB dialect actually give you this. Your table names will give you this. And when you run the db.table info, then you'll get much more details. You will have the table DDLs, you will have some sample rows as well. So now this table info is exactly what LLM needs actually to understand what kind of table structure is there, what kind of DDL is there, what all columns it is using, what kind of rows it has. So this helps LLM to actually use the natural language text to build the queries, right? And we'll see that as we move forward. So now that we have all the schema set up and we can see that the schema is coming through Langchain as well, let's see how do we build the SQL query. Okay, so to build the SQL query, we will be using a method called create SQL query chain. And before we use it, let's read a little bit about this method. So with Claude 3, first of all, you need chat Bedrock. So for the Bedrock API to work here, and you have to import Langchain AWS to work. Now create SQL chain. It creates a chain that generates the SQL queries using Langchain. Now, if you remember the SQL database class that we provided, it also have this get table info method, right? That we use to actually get the schema of the tables, and it also provided some of the sample rows and table names, etc. So just keep that in mind. Like there is keep that as a caution if you are working with a customer who has sensitive data. So there is a risk of leaking this sensitive data. So if that is the case for your customers, then make sure that you limit the permissions or maybe use vector databases or something else to actually do it other way around. Okay, so having that out of the gate, let's see how can we actually build the SQL queries. So again, we are using create SQL query chain here. For the LLM, I'm using Bedrock and I am using Claude 3 Haiku here. You can also use Sonnet. Both works really well. Haiku is a little bit faster than Sonnet. Sonnet is more intelligent and more expensive as well. So depending on the use case, if it is a complicated schema, you might find Sonnet performs better than Haiku. Um, and maybe for simpler ones, you might find Haiku is doing as good as Sonnet, but also doing it faster as well. So anyway, so I'm using Haiku for now. And with this create SQL chain, query chain, we actually provide two different parameters here. One is LLM and one is database. So LLM, here we are actually taking it from the Bedrock. And DB here, if you remember, that is a whole schema that we got from the Postgres. Okay, so we have this invoke API that we can actually invoke here, and the question that the user prompt is, how many customers do we have? Skip the preamps and print only the executable query, not the SQL query. So if you run that, you can see that it actually comes up with the right SQL queries like count star as total customers from customer table. Now the reason that we need to add these prompts here, because if I let's say if I remove this prompt and run this one more time, you will see that it has some preamps that will come as part of this SQL query, which makes this SQL query not executable. So if you pass this particular SQL query as a part of a Langchain, it will say that the SQL query is not executable and comes up with an error. So just to avoid that, let's add that and make sure that we are actually getting a fully executable query. So this all looks good. So it can generate the query. Let's see if we can actually execute the query as well. Again, we are using invoke API, and then we are running the query. Now the output is coming as 2. Again, not the greatest output here, but the good thing is that we are actually getting the query. We are also getting the output, and we'll improve the output as we move along. So looks good. So that was just a query on a particular table, one single table. Let's see if we can actually run it on a multiple tables where we need to join two different tables. So here the user prompt, I'm asking, tell me the address of the customers who order on a particular date. So the LLM needs to actually look at two different tables. One is the order table, one is the customer table. All right, so let's see if it can generate the query for us. And it can. So it gives us the right query based on the order date. It is getting the address from the customer table. Looks good. Let's see if we can execute that. And yes, and this is the address that we have for that particular customer. Okay, so two table joins, a simple one works fine. Let's see if we can try the more complex queries as well. So in this example, I'm asking, find the total sales amount for each customer, and let's run this query. Okay, so as you can see, this one does require a couple of joins here, a little bit more complex query, but looks okay. This can generate the query, no issues. We can try running it and comes up with the result as well. So yeah, looks perfect. It gives you all the customer names and their sales amount for each customer as well. Okay, let's try one more. Okay, so this is a decent complexity query for this kind of a schema. Get the details of orders that include products from more than one category. You can see there is quite a few joins that we are doing as part of this. There is also aggregate functions, having, count, and so on. But Anthropic does a good job actually in generating the query as well. So overall, it is generating all of the queries that we asked for. We may need to play around with the prompt a little bit, but it does a good job. Before we go down and see how do we actually improve the output of of the SQL, because rather than SQL output, we want to actually give the natural language looking output to the business users. So we'll see how to improve that. But before that, I just wanted to show um, what is the difference between the execution latencies between these three Claude models. So I'm using two Claude 3 model here, Sonnet and Haiku, and obviously one previous generation Anthropic Claude 2.1. So being this is going to be the slowest one, here you can see query latencies are quite high with the Anthropic Claude 2.1. Sonnet and Haiku are really fast, with Haiku the fastest model here. All right. So one thing that we wanted to improve was actually the result of the query. There are multiple ways you can do that. One is simply just using the Langchain, and whatever the query result you are getting, you can pass that query result as an input to another chain, basically to LLM, and ask it to improve that, summarize it, things like that, and it will actually provide you the better output. Another way actually we can play around with this is using the Langchain agent. And I'm actually showcasing Langchain agent here rather than the chaining of different queries, because with the Langchain agent, you can actually also look at what is going on under the hood. So it can basically, when it's think through, it actually start writing all of those steps so we can see what is going on as well. So it's very, very similar to how we used Langchain before. It's just have a little bit different SQL database toolkit here and agents toolkit. So most of the syntax looks similar. You just need to use SQL database toolkit here. And again, we are passing the database schema and the LLM here. LLM here, I'm using Sonnet. So let's run it. And we are trying to find the top 5 products with the highest sales volume by quantity sold. Okay. So you can see in the output, now it is actually going to the executor chain, right? And it is going to list down everything that it is doing. So action input, these are the tables that we had thought. Order and the order item tables likely to contain the data I need to calculate the sales volume per product. I should check the schema for those tables first. So it basically, based on the names, it decided these are the 2 tables most likely to contain the information I need. So it is actually checking the schemas of these tables. And you think, yeah, it is correct. And then it builds the query based on that. And it also think through is saying, hey, the query looks correct, so I can execute it and get the top 5 products by sales volume. Right? So it go ahead and execute the query and gives you the final answer. And it is finishing the chain. So if you see the final output, and if you're just interested in the output, so this will be the output. You will have one input, which is our user question, get the top 5 products, and then it will give you the output. There's still few nuances where you can actually remove these new lines, and this can be easily done by just modifying the prompt and adding few extra details here. And it does perfectly actually just by using an agent and doing nothing else. So it can think through step by step and give you the result that you need. Okay, perfect. So so far we have seen how to do that using Anthropic's Claude 3 model, and it was a straightforward architecture. Now, one problem that we have with this particular approach is, in this case, you are actually passing the whole database schema to the model, right? And right now we only have 5 tables, but for any of the retail customers or any other customers, when we have the databases, chances are the database will contain many more tables. Some can contain even thousands to 10,000s of tables, right? And it will become very, very expensive if we have to pass those 10,000 tables as part of the input schema to these LLMs so it can generate the sequels for us, right? So it will be too many input tokens, and invocation latency will be so much higher as well. Especially when in your database schema, your name of the tables doesn't align with what it contains, right? So that will create a lot of problems, and it has to go through the whole schema actually to generate the queries. So we have a task to how do we actually optimize this approach and how do we reduce the input tokens actually. Okay, so before we actually look through this particular architecture, I wanted to actually talk about how do you do model tracing as part of the Bedrock. And I will actually share another very short video on how to do model tracing. But it is very simple. You go to the Amazon Bedrock console, and on the left hand corner, there is a setting where you can go in and enable the logging. Once the logging is enabled, you can go to the CloudWatch and look at the trail where it will give you the details like invocation latencies, input tokens, and output tokens. Okay, so that will help us. Basically, for this kind of agent, when I looked at the trace last time, it was around 1285 tokens is what it was taking as an input token. So let's see if we can improve that. And one thing I thought of trying out with is the vector database. So here what we are doing, exactly what we were doing in the past, but with just one modification, that we are also using Aurora Postgres as a vector database in this particular architecture. So what we are doing is, rather than just LLM to actually passing all the schema to LLM and asking it to generate a SQL, we are first asking LLM to go to Aurora Postgres and do a similarity search on a particular table. Now we created one table called table description as part of this Aurora Postgres. Now this table description table contains the name of all the tables in the database and the description of all the tables, and it also contains an embedding column which is nothing but the embeddings on the description text. So basically it contains 3 columns: table names, description, and embedding column of the description text. Now, as soon as the user sends the user prompt, let's say it is saying, hey, how many customers do we have? That prompts get converted to the embeddings. LLM does the semantic search in Aurora Postgres table description column to identify the tables that are relevant for that kind of embeddings, right? So it finds the closely matching tables, returns the table to LLM, and then LLM, only using those tables, build the SQL, and then the workflow goes as it is, as we did in the last one. So what we have done here is we actually made one extra call in Amazon Aurora to do the semantic search. But by doing that one extra call, we actually probably, let's say we came up with 3 different tables that we need to build the SQL query. So in that case, we actually filtered out most and rest of the schema. So the number of input token we reduced by huge margin, right? So this is something that we wanted to try. Let's see how it works out when we build it. But here also you can track the invocation latency, input token, output tokens, and then you can compare between these two architecture, how much savings in the input output tokens you're getting, basically input tokens only as part of this particular modified architecture. Okay, so let's go ahead and build this one. So before we do that, I wanted to show you how do we actually create the table description, right? So obviously, if you have hundreds of tables in your database, it is very difficult for you to actually go in and start writing about every table, what does it have. So in this step, I just ask Claude only. So I ask the agent, hey, can you iterate over all the database table and provide me a description of the tables based on the table schema and store it in a separate Python variable. I actually went ahead and one more step further and asked it to create the PostgreSQL tables. Also give me this inserts command as command to insert these generated table names into that table description as well. So everything I asked the agent, and it gives me the perfect, almost near perfect code actually to do that. And this is the code, and I'm not going to run it one more time because it takes a lot of input output tokens, but it does gives me the table description with each table and with each of the description of this table. It also gives me the create statement for the table and everything else. So basically what we are doing here is we are creating a table description with 2 columns, table name and description column, and we are inserting into that table description based on this variable. Okay, so once we have this, one more thing that we need to do, as we discussed, is we need to add this embedding column so we can do semantic search on Aurora Postgres. So we are also adding an embedding column with a vector 1024. And why it is vector 1024 is because when you use cohere that I'm using to generate the embeddings, it will give you 1024 dimension embeddings. So you need to use that. Okay. So to generate the text embeddings first from that text data, I am using Cohere's embedding model. You can also use Amazon Titan. So there are two models in AWS. You can use either Amazon Titan or Cohere's embedding model. Okay, so once the embeddings are generated, I'm going to update this table description and the embedding columns that we added. We need to add the embeddings that we generated using this particular function, generate text embeddings. This is just one-time activity in its offline batch process to generate embeddings. So it's very, very similar to the RAG workflow that you may have seen before. So this is that embedding generation, that batch and offline process that you can do one time, and then only you need to do it when you add a new table to the database. Okay, so once we generated the embeddings, we added everything to the table description. And okay, let me do one thing. Let me actually showcase how does the Postgres table looks like. Okay, so this is our PostgreSQL database. So if you can see in the database, we have these tables that we created: customer, order items, order, product, categories, and products. And this is the new table that we created as well. And this table has three columns: table name, description, and embeddings with vector 1024, right? So if you want to see, you can actually select star from this. Again, it will not be pretty, the output, because of the embedding column, which has 1024 length of array with the floating point numbers, but it will still be okay for us to actually just look at it and understand what it is having. So here, this particular table has information about the table names. So there is the first table, customers, the description, what does it contain, the customer table, right? And then the embedding that we generated based on this particular description, right? So we pass this description to Cohere and it comes up with this vector representation of it. Now, whenever the user prompt comes in, who is looking for, let's say, the customer name or email or customer phone number, now it knows that with the embedding matching, it can actually identify which is the closest table or with which vector is actually closely matching or the nearest vector to the one that user is asking, and it can reply back saying, hey, that would be a customer table. So with that, we can actually filter out the rest of the tables. Okay, let's go back to our notebook. So here we generated the embeddings, right? Now, and we also inserted these embeddings. Now we wanted to actually see whether if we actually ask with a user prompt, if we can actually get the right tables. So here what I am doing is I am actually sending a user prompt saying which table contains information about customer, right? And if you look at this particular query, this is the query which does the semantic search. So it is selecting tables and description. It is also doing the similarity mapping or semantic search based on the vectors that has been already there in that table description table with the embedding of this particular user prompt. So the first thing that happens is this user prompts get embedded, and yeah. So yeah, here we are generating the embeddings using the user prompt. And after that embeddings are generated, those embeddings will be matched against the embeddings that is stored in the table. And based on that similarity search, it comes up with the result. So let's run this and see which table it comes up with. And this is customer. So if I change this one, let's say products, should give me a product table now. Products, right? Now, one thing I thought, like this is giving me one table, but there could be many queries in databases which can actually have multiple table joins. So how do we do that? So for that, we just converted the variable to a list variable and added a limit 3. So I honestly don't know the best way to do it right now, but to actually think about what is the maximum number of joins that you are making in your database, and based on that just increase this limit so you are selecting all of those tables that are needed to generate a particular query. Okay, so again, let's say now we are actually passing a user prompt which has multiple things. Now we are asking, tell me the customer which ordered the most expensive item, list the item price and the customer as well. So here it has to go through multiple tables. So let's see if this code can give us the right tables that we need to focus on. And it can actually, so it actually comes up with 3 different tables: order, items, orders, and customers, that are very closely matching to the user prompt that we passed. Okay, perfect. So right now, this code is working. We can actually, using the vector search, similarity search, we can identify the tables that are closely matching to the user prompt. Okay, so next what we need to do is we need to actually use these tables and generate the SQLs like we did in the past. Okay, so how do we do that? So I'm writing, I wrote a function here, generate SQL query. And in this function, I'm passing 3 variables. One is user question. So like a user prompt, right? Which is, let's say, the same prompt, which customer ordered the most expensive item, list the item price and customer name. The second thing I need to pass is the focus table. And these focus table come out from our previous function, right? Where we actually did the vector search. So we need to pass these tables. So LLM knows that I need to build the queries based on these tables. One more information that we need to pass is the schemas of these 3 tables as well. And I made this mistake where I didn't pass that first time, and LLM saw the tables, it assumed some column names of that table and came up with a SQL query, which was not executable because sometimes in customer table you might have customer name, sometimes you may have just the name, right? So it is important to pass the table schema so LLM can understand what kind of column names you have. So table schema as well. How do we get the table schema? Very, very simple. We can just write another table schema function and do a query on information schema. All right, perfect. So what is a prompt looks like now? So the prompt is using the tables, and we are passing these tables as a table string. And this is the focus table that we generated before, right? With the following schema details, and there we are taking the schema string as a variable. Generate the SQL queries to answer the following question. So we are taking the table details that we had before. From the focus tables, and we are also getting the table schema details, and then we are generating the prompt using that, and then we are asking it to actually generate the queries based on these tables and this schema. Okay, there are some variables, max tokens, and few other things that we added. Okay. And I'm also printing out here response body. So in this case, I wanted to see how much input output tokens it actually consumed. And you can also list it out directly from the response body as well. So I am actually printing that as well. So let's see if we run the query, what happens. Okay, so here it comes. Which customer ordered the most expensive item? So this is the prompt, like this is the user question, sorry. List the item, price, and the customer name. Okay. Now, I am also printing the focus table. So it actually gives me, these are the 3 tables that LLM should focus on. Now let's see what is the prompt that was sent to the model this time. So the prompt that was sent is using only these tables. Now I have to replace that table variable, remember, order item, orders, customer, with the following schema details, and it is giving the schema details of these 3 tables. Now it is asking, generate a SQL to answer the following question: which customer ordered the most expensive item, right? So if you see the length of this particular prompt, it is only this much, which is very, very small. It's much, much smaller than the one that was last sent to the LLM through the agentic workflow when we did not use the vector search. Okay, and maybe I should actually show you that as well. So I will actually see if I can find that trail and show you that how much it was taking the last time. Okay, so this is the model response. And obviously with the query, it actually respond back with the right query. It is also actually populating here that how many input tokens and output tokens it took. And it took only 183 input tokens here. So if you take this one and put it in any model like GPT-4 or Anthropic or Perplexity and ask it to actually find you the input tokens, it will give you around close to 183 tokens here. And then it will give you the generated query and the query result as well. So obviously this one, it is reduced by 10 times. So it was 1200 before without the vector search, because it has to pass on information about order item, customer, all of that. Now it actually reduced to 183 with the vector search and with the right tables and schema information. You still get the right query and you still get the right result. Now again, all of this you don't need to print it. You can just print the output in a more natural language way. Very, very easy to do it using the prompting. But this one I wanted to actually showcase how it is thinking through and how it is actually reducing the input token counts. One last point, if you would think about from 5 tables, it is 10% gain. Think about when we have hundreds of thousands of tables in a customer schema. This will be really, really fast and really, really cost effective as well. Okay. One last thing that I wanted to show you is Streamlit application. So let me see if I can build that. So the one thing that is there with this particular code, if you basically wanted to share a demo with your customers or wanted to actually showcase some kind of a GUI where you can play around with the queries, prompt and all, this notebook isn't the best way to do it. It's a lot of code, lot of interior details that many people don't need. So Streamlit is a very good way to actually build kind of a wrapper around these and have a very nice looking UI, very, very simply as well. So I built this one. Let me actually share this. As soon as I run this, it comes up with this particular screen. And all of this code is actually the same code that I use for Jupyter Notebook. I just converted that code to Streamlit application and I'm putting it as part of the Visual Studio now. Very easy to do. You can use any LLMs to convert the code. There are also some tools that can help you convert that code as well. Okay, but you can see here it's nice looking UI. Now I can see interact with it. I can get the table counts here. This is something we tried on the notebook as well. Now 76. It is giving me the database dialect as Postgres. It is giving me the table names. I removed the schema information, which was way too much. You can actually change these prompts. You can change the query and it will give you the different query as well. So if I run this, it will execute it and give you the right query. So here is the query. Remember, we didn't put actually the prompt avoiding techniques here, so the preamps is coming. But if you put this, skip the preamps and run this query again, it will run, it will generate the query, and this time it will not give you the preamps that we had before. So basically, you can dynamically interact with it and easily showcase that how you can generate these queries in really easy way, right? Now, obviously, some customers might be interested in just the natural language looking answer, so that is something easy to achieve as well. with agentic workflow, or you can chain those things and the prompt around it as well. So let's say if we are doing get the top 5 products with the highest sales volume, and this is just the agent I'm using under the hood, nothing special. I'm not using any prompting techniques or anything, but you can see it will give us a very decent output actually. That's completely shareable with business users. All right, here it produces the query results. It gives you the input. This was the question, because gives you the output in a very nicely written way. These are the top 5 products with the highest volume quantity sold, 1, 2, and 3. So with no prompt engineering, nothing else, you get this result, which is acceptable to most business users, but you can always improve this as well. And this is kind of a latency. Everything that you did in Notebook, kind of, you can also do it here as well and showcase um, to your customer as part of the demo. All right, so that's all I have actually. Let me see if I can find you that um, one trail that I wanted to show you, CloudWatch. Okay, so this is how it looks like. The Bedrock CloudWatch trail when you run through it. So you will see for the agentic workflow, this was the prompt that was sent to the LLM. And you can compare how much did we reduce here. So this was the whole prompt where we are sending bunch of information, table information, schema information for many tables to get the result, right? And towards the end, you can also see the input tokens, how many you are passing, which was quite high, 1,000 something. Actually, it was 1,200 for that particular query, but yeah, so 1,000 tokens and output tokens you can see as well. What I'll do is I'll actually make a very short video and showcase how do we enable the tracing, and you can see it in CloudWatch as well, so that you can easily compare the input output tokens as well. Okay, that's all. Thank you so much for watching. I hope it was helpful. Let me know any feedback, any suggestions that you have, and have a great day. Thank you.